Welcome to the Deep Dive, your science corner for the intellectually curious. Today, we're diving headfirst into, well, one of modern physics' most radical ideas.
A really fascinating proposition.
Exactly. What if gravity isn't fundamental? Not that primal pull we all imagine, but something that just sort of emerges from the universe itself. Our mission here is to explore entropic gravity. It's a concept that really could reimagine how we understand the force that, keeps us grounded.
And guides the planets. It challenges a lot.
We're going to unpack how it tries to link gravity to information, to disorder, maybe even rewrite things like dark matter.
That's the potential, yes. We'll be looking at the key papers, some experimental work, the whole landscape, really.
And we've got an expert guide right here to help us synthesize it all.
It's definitely a journey into foundational physics, asking some very deep questions about reality itself.
Okay, let's start with Chapter 1. This really radical idea of gravity born from thermodynamics. It seems like the seeds were sown back in the 70s with Jacob Bekenstein.
That's right. Bekenstein made this astonishing observation about black holes. Their event horizons, the point of no return, they behave strikingly like entropy, like the measure of disorder in a system.
Which is weird, right? Entropy usually relates to volume, not area.
Precisely. He proposed that a black hole's entropy is related to the area of its event horizon. Totally unexpected.
And what's so fascinating, as you said, is how these early black hole ideas started hinting at something bigger.
Exactly. A potential link between gravity and thermodynamics just hiding there. Then Stephen Hawking jumped in.
Right, showing black holes aren't perfectly black, they radiate.
They radiate heat, yes. They have a temperature like a thermal object, which was another huge piece of the puzzle.
And then the Unruh effect adds another layer, something about acceleration.
Yes, the Unruh effect.
Yeah.
Imagine you're accelerating constantly, even in totally empty space. Unruh showed you'd perceive yourself as being surrounded by a warm glow, a heat bath. So acceleration itself seems to generate temperature.
Wow, okay. So acceleration equals heat, in a way.
In a very deep sense, yes. And that connection proved absolutely pivotal for what came next.
Which brings us, I suppose, to Eric Verlinde in 2010. He took these threads
and wove them into something audacious. He basically claimed gravity is not fundamental, it's emergent, a thermodynamic phenomenon.
How did he argue that? What were his key points?
Well, he proposed a couple of key postulates. First, imagine a kind of boundary in space, what he called a holographic screen.
Like an imaginary surface?
Sort of. He proposed that when a particle gets close, within about a Compton wavelength, the entropy on this screen changes by a specific amount.
Okay.
And he used an analogy like osmosis. Particles move towards the screen not because they're pulled, but because it's entropically favorable. The universe is pushing towards maximum disorder.
So it's not a pull, it's more like a statistical tendency.
That's the core idea. And here's the really audacious leap. He didn't just say there's a connection. He actually derived Newton's second law, EFMA.
He derived EFMA from thermodynamics.
Yes, using the Unruh temperature we just talked about and his entropy change postulate, EFMA just falls out.
So gravity, the force we feel, might just be the universe trying to get messier, statistically speaking.
That's the essence of it, a collective push from unseen information bits on the screen, driving towards higher entropy.
That really turns things on their head.
It certainly does. And he didn't stop at EFMA. He went on to derive Newton's law of universal gravitation, too. The inverse square law, FGMMRY.
How did he manage that?
He imagined this holographic screen was made of tiny information bits, almost like pixels. Then he used a principle called equipartition. Basically, in a system at some temperature, energy gets shared equally among all its components, or bits.
Right.
Applying this to the energy of a mass m near the screen, well, it led directly to Newton's GMMR law. He even started trying to extend it to Einstein's general relativity.
Okay, so that's the initial, incredibly bold proposal. Gravity as an illusion driven by entropy. But physics isn't usually that straightforward, is it? Big ideas face big challenges.
Almost inevitably. And Verlinde's idea, while elegant, ran into some serious scrutiny pretty quickly. There was a key paper, A Challenge to Entropic Gravity, by Rovido and Munoz, that really dug into the mathematical details.
What did they find? What were the main criticisms?
The core issue was uniqueness. While Verlinde's postulates allowed for Newton's law of gravity, they didn't demand it uniquely.
meaning other equations could also fit his starting points.
Exactly. They showed you could modify the standard equation for Newtonian gravity, the Poisson equation, in ways that still satisfied Verlinde's integral relationships, but these modifications were often, well, physically unacceptable alternatives.
Ah, so the path wasn't as narrow as it first seemed. It could lead to unwanted destinations.
Precisely. And this wasn't just a problem for the Newtonian case. The same issue cropped up when trying to get to Einstein's general relativity.
So you could add extra, maybe unphysical terms, and Verlinde's framework wouldn't rule them out.
That's the crux of it. It significantly weakened the claim that this could be a complete replacement for gravity as a fundamental force.
Were there other specific worries?
Yes, several. Like combining classical ideas like equipartition with the quantum unruh temperature without adding necessary quantum corrections.
Mixing classical and quantum can be tricky.
Very. Also, some specific mathematical solutions seem to predict zero temperature, which violates the third law of thermodynamics, and the entropy area law he relied on. It turns out it's not exclusive to Einstein's theory. Other theories can have it too.
What about things like the cosmological constant, the expansion of the universe?
That was another difficulty. It wasn't immediately clear how to naturally incorporate the cosmological constant within his original framework, unlike some other thermodynamic approaches to gravity.
So if these challenges were so significant, what happened next? Did people just say, okay, interesting idea, but it doesn't quite work?
Not quite a dead end, no. In physics, critiques like these often spur new thinking, different angles. It showed the limitations, yes, but it didn't kill the underlying fascination with the gravity-thermodynamics link.
It just meant the original formulation needed rethinking or maybe a completely new approach.
Exactly. And that's what we're seeing now. It's sort of second wave, exploring this connection in new ways.
Right, which brings us to some really exciting recent stuff, like Professor Ginestra Bianconi's work from Queen Mary University, just out this year, 2025. She's proposing gravity comes from quantum relative entropy. What is that?
Quantum relative entropy. Okay, it's a concept from quantum information theory. Think of it, roughly, as a way to measure how different or dissimilar two quantum states are.
Okay, like a distance measure for quantum stuff?
In a sense, yes. Bianconi treats space-time itself, the geometry described by the metric, as a quantum operator.
Whoa.
And gravity, in her framework, emerges from the dissimilarity between this quantum space-time metric and another metric induced by the presence of matter. It's a difference, a kind of informational distance that manifests as gravity.
And this leads to modified Einstein equations.
It does. Equations that look like standard general relativity when gravity is weak or curvatures are small.
Which is good. It matches what we observe locally.
Exactly. But they diverge from GR at very large cosmic scales.
And this divergence is where it gets really interesting, right?
Yeah.
Because you mentioned dark energy and dark matter.
This is potentially huge. Her theory naturally predicts a small, positive cosmological constant.
The thing driving the universe's accelerated expansion. Dark energy.
Precisely. It seems to fall out of her equations, potentially explaining dark energy from these quantum information principles. That's a major goal in physics.
Wow. Okay. And dark matter.
Even more intriguingly, her modified equations include an extra component, an auxiliary field she calls the G field.
Okay.
This G field is just part of the mathematical structure, but Bianconi suggests it might actually be dark matter. Not a particle, but some kind of inherent geometric effect predicted by the theory.
So potentially solving two of the biggest cosmic mysteries in one go. From first principles, that is a big deal.
It's certainly a very bold and exciting proposal. It connects gravity, quantum information, dark energy, and dark matter in a novel way.
Has there been any observational evidence, even hints, pointing in this direction? Maybe related to Verlinde's earlier ideas about modifying gravity instead of needing dark matter?
There have been some interesting findings. Back in 2016, Margot Grauer's team looked at gravitational lensing, how mass bends light from distant galaxies.
Right. Lensing tells you how much mass is there, whether you can see it or not.
Exactly. They compared the observed lensing with predictions from two models, standard models using dark matter, and a model based on Verlinde's ideas, specifically a form of modified Newtonian dynamics, or MOND, which tries to explain galactic rotation without dark matter.
What did they find?
Surprisingly, both models could fit the data reasonably well, but the Verlinde-inspired MOND model seemed to require fewer adjustments, fewer free parameters to match the observations.
So maybe a hint that modifying gravity might be a simpler explanation than invoking invisible matter.
It's tentative, certainly, and only one study. But it does provide some empirical food for thought, suggesting the phenomenology, the observable effects of emergent gravity might align with what we see, especially regarding dark matter effects.
It's not just theory, then. There are observations being brought to bear.
Yeah.
And now there's even work trying to build concrete models and think about lab tests, like Daniel Carney's work.
Yes, Carney and colleagues at Lawrence Berkeley, also very recently, are trying to build tangible mechanical models. Picture gravity literally as a push caused by random interactions of tiny fundamental quantum bits, or qubits.
Qubits, like in quantum computing.
The fundamental idea of a two-state quantum system, yes. They have a couple of models. One is like a crystal grid of these qubits. A mass nearby creates a region of lower entropy, a pocket of order, and the surrounding system effectively pushes on it, trying to compress this low entropy region to maximize the overall disorder. That push is gravity in the model.
Okay, that's one picture. What's the other?
The other involves non-localized qubits, their ability to store energy changes depending on how close masses are. The system finds it entropically favorable higher entropy for masses to be closer together, again, leading to an attractive force.
These sound quite simplified, maybe ad hoc, as they say.
They are, and they currently only reproduce Newtonian gravity. But their value isn't in being a final theory. They're a proof of principle. They show it's possible to build models where gravity emerges like this.
And crucially, they might suggest ways to test the idea.
That's the exciting part. These models predict something specific if you put a mass into a quantum superposition existing in two places at once.
Which physicists are trying to do with larger and larger objects.
Right. The interaction with these background qubits, according to the models, would quickly destroy that superposition. It would snap the object out of it.
So it makes a testable prediction about quantum mechanics at macroscopic scales.
Exactly. And this prediction connects directly to ongoing experiments, like those by Angelo Bassi's group in Trieste. They're already trying to test models where the quantum wave function collapses spontaneously.
Ah, so those experiments, designed for something else, might also be probing entropic gravity indirectly.
Potentially, yes. It offers a rare and exciting chance for experimental feedback in a field that's often highly theoretical. Imagine an experiment telling us if gravity is fundamental or statistical. Mind-blowing.
It really is. So putting it all together, entropic gravity, especially newer versions like Bianconi's, is aiming high, trying to be a route to quantum gravity, treating gravity as emerging from quantum information. How does this fit in the bigger picture? Because general relativity is still the reigning champion, right?
Absolutely. It's crucial context. Entropic gravity is just one player in a larger field of alternatives to general relativity. There are others like scalar tensor theories or MOND and its relativistic versions like TeVas. Many are trying to solve the dark matter-dark energy puzzles without new particles.
But GR has passed every test thrown at it so far.
With flying colors. Classical tests like light bending, gravitational redshift, the orbit of Mercury, precision tests using the parametric post-Newtonian formalism, and strong gravity tests like observing gravitational waves from merging neutron stars, GW 17087
That last one confirmed gravitational waves travel at the speed of light,
Right.
Which ruled out a lot of alternatives.
It did. It put very tight constraints on theories where gravity travels differently. The more precisely GR is confirmed, the less wiggle room there is for alternatives. They often get, as physicists say, squashed towards zero.
So it's a tough path for any new theory. It has to match GR where GR works perfectly and solve the problems GR doesn't address.
It's an incredibly high bar, which is why entropic gravity, for all its conceptual appeal, is still seen as a long-shot idea by many, a minority view.
But one that won't die, as you mentioned.
Because the core idea, the connection to thermodynamics and information, remains deeply compelling. And the puzzles it tries to solve are real and fundamental. But skepticism is healthy and necessary. Any new theory must be consistent, complete, match all observations, and not create new problems.
So we've gone from black hole thermodynamics in the 70s through Verlinde's bold proposal, the challenges it faced, and now these new quantum information approaches like Bianconi's, maybe even hinting at experimental tests.
It's been quite a journey, showing how ideas evolve in physics. Entropic gravity offers this alternative perspective. Gravity not as a fundamental force, but emerging from the universe's tendency towards disorder, towards higher entropy.
And for you, the listener, think about that. The force holding you in your chair might not be a fundamental law, but more like a statistical tendency, a consequence of deeper, unseen information processes.
It really changes how you might perceive space, time, and reality itself. And it offers this fresh lens on those big cosmic mysteries, dark matter, dark energy. Could they be solved not by new stuff, but by a new understanding of gravity itself?
Which leads to a final thought to mull over. If gravity, this seemingly fundamental force, could actually be an illusion, a collective effect, well, what else might be? Are other fundamental forces potentially emergent too? Are more parts of our everyday reality just reflections of a deeper, information-based universe?
It certainly gives you something to think about.
Indeed. Something to ponder until our next deep dive.